Hello, welcome to Unit 6, Lesson 2, How Does It Change? Let's take a look at the first activity. In this activity, it says, how does each expression represent the number of small squares in the figure? For expression A, it says 6 times 8 minus 2 times 3. Expression B says 4 times 8 plus 2 times 5. Expression C says 8 plus 8 plus 8 plus 8 plus 5 plus 5. Expression D says 5 times 6 plus 3 times 4. So take a look at the figure on the left and try to connect these expressions to this figure. Pause the video and work on that. All right, let's take a look at expression A. So this expression comes from there being 6 rows with 8 small squares. So that's the 6 times 8. But from this, two rows of 3 small squares have been removed. So let's take a look a little bit deeper at that. So 6 rows, so we can see here's the 6 rows, 1, 2, 3, 4, 5, 6, of 8, 1, 2, 3, 4, 5, 6, 7, 8. But we see this section right here has been removed, and that section is made up of 2 rows. And if I were to draw in those squares, I would see each row would have 3 squares. So that is all being removed. All right, let's take a look at the next expression. So this one is 4 by 8 plus 2 by 5. So this one is saying there is 4 rows of 8 small squares and 2 rows of 5 small squares have been added to this. So let's take a look at that. So the 4 rows of 8 small squares are right here. So 1, 2, 3, 4. And then we're adding in this section right here, and that's 2 rows. And there's 1, 2, 3, 4, 5 in each row. Okay. Let's take a look at C. So this one says 8 plus 8 plus 8 plus 8 plus 5 plus 5. So this one is just you're counting each row starting from the bottom. So I can see that. I have 8 here, 8 here, 8 here, 8 here, and then 5 here and 5 here. So I'm just adding all those squares up. Okay, let's take a look at the last one. Okay, this one, 5 times 6 plus 3 times 4. So this one is looking at columns instead of rows. So we are saying there are 5 columns of 6 small squares and 3 columns of 4 small squares. So if we look at the picture, here's 1, 2, 3, 4, 5. Those have 1, 2, 3, 4, 5, 6 in each one. And then we have 3 columns with 1, 2, 3, 4 in each one. So that's it for this cool down. Just seeing that there's many different ways to kind of take a figure like that and write a mathematical expression that represents it. Let's go ahead and take a look at the next activity. For this activity, we see 2 different patterns. For the first pattern, we see step 0 starts with 1 dot. Step 1 has 3. Step 2 has 5. And then step 3 has 2, 4, 6, 7. Pattern 2 shows step 0 as no dots. Step 1 with 1 dot. Step 2 with 4 dots. And step 3 with 9 dots. So question 1 asks you to study the 2 patterns of the dots and then describe how they're changing and how would you find the 5th number in each pattern. Question 2 has you then completing a table of values to describe the number of dots in each pattern. Step 3, question 3 wants you to then graph them and then explain why you know the graphs look the way they do. So go ahead, pause the video and work on that. All right, let's take a look at question 1. Let's analyze each pattern. So for pattern 1, we see that each step level has 2 rows of dots plus an additional dot. But the 2 rows that exist match the step number. So if we ignore 0 for a second, because that's a little bit harder to see, and start with step 1, here's 1 row, here's a 2nd row, they both have 1 dot in it, and then we have an additional dot. In step 2, here's 1 row, here's a 2nd row, they both have 2 in it, and then here's an additional dot. Step 3, here's 1 row, here's the other row, they both have 3 in it, here's our additional dot. So pattern 1 each step has 2 rows with the same number of dots as the step number plus 1 additional dot. So if we were to analyze step 5 for pattern 1, that would tell us that step 5 would have 2 rows of 5 dots plus 1 additional dot. So just to show you what that would look like, it would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then we would have our additional dot right here. So that's step 5. Okay, let's take a look at pattern 2. So for pattern 2, each step has as many rows and columns as the step number. So step 0 has nothing. Step 1 has 1 row by 1 column. Step 2 has 2 rows by 2 columns. Step 3 has 3 rows by 3 columns. So this is pattern 2. Each step has as many rows and columns as there are steps. So what will step 5 look like? Well, you guessed it. It's going to have 5 rows and 5 columns. So let's draw what that would look like here. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that is again step 5. All right, let's go ahead and fill out our table. For pattern 1, step 0 had 1 dot, 1 had 3, 2 had 5, 3 had 7. So now, if we think about step 4, there were 2 rows of 4, so that's 8, plus 1 more is 9. For step 5, we had 2 rows of 5, so that's 10, plus 1 more is 11. Step 10 is going to be 2 rows of 10, which is 20, plus 1 more, which is 21. So if we think about the type of relationship this is, it's a linear relationship. As x increases by 1, I can see y is increasing by 2. So here we have plus 1, plus 2 each time. So I know that my slope is 2, because 2 over 1 is 2. But this is not a proportional relationship, because if it was proportional, step 0 would also have 0. So I need to take into consideration my y-intercept. Remember, this is going to represent your y-intercept because it crosses the y-axis at 1. So my expression is just going to be 2n plus 1. Let's take a look at pattern 2. So pattern 2 had 0 at step 0, had 1 at step 1, 4 at step 2, 9 at step 3, and hopefully you've guessed the pattern by now. There's going to be 16 at step 4, 25 at step 5, and 100 at step 10. Basically, we're squaring the step number, right? So this is not linear. This is non-linear, meaning there is no slope. So remember, we talked about that, right? There's only slope for linear equations or linear expressions. So we have to think about how we could represent this for any given step number. So if our step number is n, to figure out the number of dots, we're just doing n times n. Or another, excuse me, another way to write that is n squared. Let's go ahead and take a look at what those graphs look like. So starting with pattern 1, so I know step 0 had 1, which is about here. 1 had 3, which is going to be about there. 2 had 5, which is about there. 3 had 7, so we'll say that's about there. 4 had 9, so that's about there. 5 had 11, it's about there. So we know 6 will have 13, which is about there. So we can see that it does show that linear relationship, right? Sorry, my line is not straight. But it does show that it's linear. We can see the points form a straight line. Obviously, it's a little off because it's a little bit harder to graph points that aren't on grids, but we can see that it is straight. Let's take a look at the next one. So 0 was 0, 1 was 1, 2 was 4, 3 was 9, 4 was 16, 5 was 25, then 6 will actually be off the graph. This one, we can tell, is not linear. It almost appears to be exponential. But we know it's not exponential, right? Because we've learned how exponential equations have the exponent in the variable in the exponent, but our expression shows a variable, our number in the exponent. In fact, the number 2 in the exponent. So hopefully you've recalled back to when we looked at the 3 different types of functions that we would be focusing on this year. And we talked about linear, we talked about exponential, and there was one other one called quadratic. So hopefully by now you're making that connection to the 2 types, or to this pattern specifically. Question 4 explains why, says to explain why the graph of the 2 patterns look the way they do. So The points representing the first pattern lie on a line because getting from one step to the next step involves adding the same number of dots, right? We talked about how that shows a linear relationship. So pattern 1 is increasing at a constant rate, so it makes sense that the graph is linear. Pattern 2, on the other hand, for pattern 2, it makes sense that it's more of a curve because it's not increasing at a constant rate, is not increasing at a constant rate. The number of dots being added each time is increasing. So we should see a curve. All right, let's go ahead and take a look at activity 3. In this activity, you're given another 3 steps, that there's a pattern, and then you have the first question asks if the number of small squares is growing linear, and how do you know? Then it wants you to complete the table, and then question 3 says, is the number of squares growing exponentially? How do you know? So go ahead, pause this video, and complete those 3 questions. So let's first analyze the 3 steps. So in step 1, we see there are 3 squares. There are 3 squares. Oops, let's use different color. 3 squares. Step 2, there are 6 squares. Step 3, there are 11 squares. So right off the bat, we know it's not linear because if it was linear, we would be adding the same number each time, right? Here to get to 6, we have to add 3, but to get to 11, we have to add 5. So question 1, we know it is not a linear relationship because it is not increasing at a constant rate. So now we need to figure out, well, what is the pattern that these squares are increasing by? And again, step 1 is a little bit hard to tell, but if we compare step 2 to step 3, just looking at the visualization, what I pick up on is that there's a square inside here, and that square's row and column matches the step number, right? Again, same thing here. There's a square that has a 3 by 3 array. We call that array. It's a 3 by 3 square. You could even go back to step 1. That's a 1 by 1 square. So we can see that that inner square is made up of the step number to the second power, right? 1 to the second power is 1, 2 to the second power is 2, and 2 to the second power is 4, 3 to the second power is 9. We also see that there are 2 additional squares continuously being added each time. So not only are we taking the step number and squaring it, but we're also adding 2 more to that quantity. So for step 1, since we know there's 3, Step 2, there was 6. Step 3, there was 11. So we can assume for step 4, if we square that, we have 4 times 4, which is 16. And then we add 2, which is 18. 5 times 5 is 25, plus 2 is 27. 10 would be 10 times 10, which is 100, plus 2 is 102. 12 would be 12 times 12, which is 144, plus 2 is 146. So I can represent that as an expression by doing n squared plus 2. The last question says, is the number of small squares growing exponentially? Explain how you know. So other than noticing the n squared, we can dive in deeper to see if there's a growth factor, right? In order for it to be exponential, if we take a term and divide it by the previous number, that is our growth factor, and it should stay consistent. So for example, when I do 6 divided by 3, I get 2, but 11 divided by 6 is approximately 1.8. So right away, we can see that the growth factors are different. So it can't be exponential. So not only do we see that the number of squares are doubling each time and then adding an additional 2, we can also see that there is not a consistent growth factor. So the number, wait, get it right, no, the number of squares are doubling and adding 2. Also, there is not a consistent growth factor. In fact, this relationship for this pattern is called a quadratic relationship. Now, in our previous lesson, we learned that quadratics are expressions where the biggest exponent is 2. So this is the perfect example of a quadratic relationship. So quadratic relationships are different from linear relationships because as one quantity increases by a certain amount, the second quantity does not increase by the same amount. So there's no constant rate of change, i.e. no slope, okay? And it's not like a exponential relationship because in exponential relationships, as one quantity increases by a certain amount, the second quantity changes by the same factor. So again, no constant growth factor. So it is a different type of relationship from the two that we have worked with so far. But again, we kind of previewed that prior to starting exponents. We previewed what quadratics would look like. So that's it for this lesson. Thanks for watching.